in the previous lecture we have discussed the problem of symmetric potential well. Actually, in a infinitely deep symmetric potential well, a particle of mass m was confined, and we have find the eigen state and the energy eigen value in that condition. Now, in this lecture, we are going to solve a very important problem based on this idea. You can see the problem says that a particle of mass m is subjected to a potential v of x equal to 0 when x mod of x is less than a by 2, and it is infinity when mod of x is greater than a by 2. This is the simple description of a symmetric square well potential. Now, we have to find the ground state, the first excited state, and the second excited state wave function first of all. Then you have to find the energy in the first in the ground state, in the first excited state, and in the ground state, and in the first excited state, and then in the second excited state. And we have also to find the probability densities P1 of xt and P2 of xt. It means that we have to find the probability density at time t in ground state and also in first excited state. And after that, finally, we have to find the expectation value of the position when n equal to 1 and when n equal to 2. So now let us see how we can solve this problem. Actually, you can see the potential description is nothing. It is simply the square well potential of infinite depth, and so you can see this figure. This is just a symmetric square well potential of infinite depth, and its width is equal to a, and potential in the region x equal to minus a by 2 to plus a by 2 is 0, and beyond that region it is infinity. So it is obvious that the particle is confined in an infinite symmetric well potential of width a. And as we have seen in this case, actually the eigenfunctions may be even or may be with odd parity and also with even parity. So you can see in this condition that the eigenfunctions are psi n of x equal to a square root of 2 by a cos n pi x over a, where n equal to 1, 3, 5 and so on. In fact, this is the eigenfunction with the even parity, and this is equal to root over 2 by a sin n pi x over a, where n equal to 2, 4, 6 and so on. These are this is actually the eigenfunction for the even parity, odd parity. Now you know that in this condition the energy eigenvalue is given in this manner. This is En equal to n square pi square h bar square over 2ma square. So all these results I have just written directly from the idea which we have developed in the previous lecture while dealing with the symmetric potential well problem. So remember these expressions because this should be written here directly. Now you can see in the first part of our problem we have been asked to find that what will be the eigenfunction in ground state, in first excited state and in second excited state we have to actually find. So let us find the ground state, eigenfunction. You know, when we will consider the ground state, we will take n equal to 1. And so you can see when n is equal to 1, then actually the eigenfunction is in terms of cosine function, and so we should write psi1 of x, psi1 of x, this will be equal to a square root of 2 over a cos n pi x over a, but n is here 1, so this will be pi x over a. This is actually the ground state eigenfunction. Now we will find the first excited eigenfunction, for which we will take n equal to 2. So first excited state eigenfunction, first excited state eigenfunction. This is given as psi2 of x, and you can see when n is 2, then eigenfunction is in terms of sine function. So this will be what? This is a square root of 2 over a sine 2 pi x over a. Now finally we will find the eigenfunction for the second excited state. So second excited state eigenfunction, second excited state eigenfunction. This will be psi3 of x, and you can see when n is 3, then again the eigenfunction will be in terms of cosine function, and so you should write this is a square root of 2 over a cos 3 pi x over a. So these are actually the eigenfunctions in these first 3 states of the particle. This psi1 of x is ground state eigenfunction, psi2 of x is first excited state eigenfunction, and psi3 of x is the second excited state eigenfunction. Now let us see what is problem B. In part B of the problem, we have to find the energy eigenvalue for the first 3 states of the particle. That is, we have to find E1, E2, E3 and E3. So let us see this expression. Simply we will take n equal to 1, 2 and 3 in this expression 2, and we will get the energy eigenvalue E1, E2 and E3. So this is very simple. You can see E1. When I am just writing here again that expression for your convenience. You have seen that En is equal to n square pi square h bar square over 2ma square. So now let us find E1. When you say E1, it means you take n equal to 1. So this will be simply pi square h bar square over 2ma square. Then E2, now we will take n equal to 2. So this is simply 4 pi square h bar square over 2ma square. Then E3, and for E3 we will take n equal to 3. So this is 9 pi square h bar square over 2ma square. 2ma square. Now see what is the third part of our problem, and what we have to find in this third part you can see here. In third part of the problem we have to find the probability densities at any time t in the first two states of the particle, that is in ground state and also in the first excited state. Now we know how probability density is defined. You know that probability density is simply the square of the mod of the eigenfunction at any time t. So for this we will first of all find these eigenfunctions psi1 of xt and psi2 of xt at any time t. So now you know how time evolution we consider. You know that psi1 of xt, this is actually given as psi1 of x0, or you may simply say psi1 of x e raised to the power minus I e1 t over h bar. But you know what is this psi1 of x0? This is a square root of 2 by a cos pi x over a times e raised to the power minus I e1 t over h bar. So this is psi1 of xt. Similarly, first of all we will calculate psi2 of xt. So psi2 of xt is what? You can write psi2 of xt equal to psi2 of x0, or you may simply say psi2 of x, and times e raised to the power minus I e2 t over h bar. Now let us substitute the value of psi2 of x. This is in fact a square root of 2 over a sine 2 pi x over a, and times e raised to the power minus I e2 t over h bar. Now from the definition of probability density you can now easily calculate what will be the probability density of the particle to be in ground state. So if this probability density is p1 of xt, then this will be simply equal to mod of psi1 of xt square, and this mod of psi1 of xt square, this will be written as psi1 star of xt times psi1 of xt. But you can see that psi1 of xt is real, so its complex conjugate psi1 star of xt will remain same. So this is simply root over 2 over a cos pi x over a, and times psi1 of xt. This will be again root over 2 by a cos pi x by a, and this can be written as 2 over a cos square pi x over a. So this is the probability density p1 of xt. Similarly, we can find the probability density p2 of xt. So now let us calculate it. You know p2 of xt will be what? This will be mod of psi2 of xt square. and this is psi 2 star of xt times psi 2 of xt. And now let us substitute the values of these, and substituting these you can easily see this will be simply 2 over a sine square 2 pi x over a. So these are the probability densities P1 of xt and P2 of xt. Now let us see what is the fourth part of the problem. In fourth part of problem you can see we have to find the expectation value of position when the particle is in its ground state and also in the first excited state. So finally we will calculate these expectation values. So you have already studied in the previous lectures how we find the expectation value of any operator. So here actually there is position operator, and you know position operator is simply multiplication by x. So the expectation value of x in ground state, you know this is in fact equal to integral minus infinity to plus infinity psi 1 times psi 1 star times x times psi 1 dx, because you know that this function psi 1 of x is normalized. So in the factor in integral, which is psi 1 star times psi 1 dx, this is actually equal to 1, because psi 1 of x is normalized. So this integral in denominator will be 1. So you can write this is minus infinity to plus infinity psi 1 star times x psi 1 dx. Now you know in this case actually these limits minus infinity to plus infinity implies all space, and in our present problem our all space is lying between x equal to minus a by 2 to x equal to plus a by 2, because you know that particle is confined in this potential well. So actually here the limits will be from minus a by 2 to plus a by 2. So let us substitute it. This will be minus a by 2 to plus a by 2. Now psi 1 star is what? You know this is simply root over 2 by a cos pi x by a times x times, again this is root over 2 by a cos pi x by a, because you know that psi 1 of x is actually a real function, so its complex conjugate remains same. And now let us simplify it. So expectation value of x in the ground state is equal to, this will be 2 by a integral from minus a by 2 to plus a by 2 x times cos square pi x over a. Now you can easily see that this function in x is actually an odd function, and cos square pi x over a is an even function, and you know the product of the even and odd function is actually an odd function. So this product is an odd function, And if it is in our integrand is an odd function and limits are from minus a by 2 to plus a by 2, then you know from calculus that this integral will be simply 0. So you can say that this is odd function, and hence we can write that expectation value of x in the ground state, this will be 2 over a into 0, and so this is equal to 0. Now we have also to find the expectation value of position x in the first excited state. That is, we have to find expectation value of x in state 2. So what will be this? Again you can see this will be in fact 2 over a integral minus a by 2 to plus a by 2, and here we will take the eigenfunction of the first excited state, and you can see the eigenfunction of first excited state is this much. So I have taken this 2 by a factor, which will be multiplied 2 times outside of the integral, and there will be sine square 2 pi x over a. So this is x times sine square 2 pi x over a dx. And again you can see that this integrand is an odd function, because x is an odd function and sine square 2 pi x over a is an even function. But we know the product of an odd function and an even function is simply an odd function, and so this result will also vanish. Therefore you can say that expectation value of x in the first excited state, this will be 2 over a times 0, and so this is 0. So in this way you have seen how easily we can solve the problem based on the concept of symmetric potential well. But for this you must remember the eigenfunction and the energy eigenvalue for solving such type of problems.